Hello everyone, just continuing where we have left in our previous video lecture. So earlier what we have seen is that we have seen simple benefit to cost analysis where we have only one alternative, and on the basis of benefit to cost analysis we are making calculations to make decisions whether to accept that particular project or not. Now that is the case where we have only a single project and we are basically comparing that particular project with no project kind of condition. Now if we have two different mutually exclusive alternatives available with us, then how do we extend this benefit to cost analysis to select from among the two the best feasible project? So that can be done with the help of what we call as incremental benefit to cost analysis. So again, the basic criteria is the higher cost alternative is justified only in case where we have the difference between the benefit to cost is equal to or larger than 1, or we can say it's greater than equal to 1. That is, if we have the incremental benefit to cost ratio greater than equal to 1, only then the higher cost alternative is to be chosen. Otherwise we will stick with the lower cost alternative. Now the thing is that whenever we are making calculations regarding two mutually exclusive alternatives, we have to arrange the alternatives in an increasing equivalent on the basis of increasing equivalent total cost. If we are computing on the basis of present worth, then the first we will pen down the project which is having the least cost, then the second will be the project with a higher cost, and next higher, and so on and so forth. So the thing is, what we are doing, we are comparing one project with the another, and on the basis of the incremental benefit to cost ratio we are making decision about the acceptability of any one of the project. Now the process is somewhat what we have discussed in part 1, that is lecture in part 1. But here what we do, first of all, on similar lines we will determine the equivalent total cost for both the alternatives using present worth or annual worth or future worth equivalencies that we have done in the previous case also. Order the alternatives by equivalent total cost, that is the least cost will be written first, and the highest equivalent, the project, the cost associated, the highest cost associated the project, that project we will write at the last, that is first smaller then larger, so on and so forth. Then what we do, we calculate the incremental cost, that is delta C, for the larger cost alternative. If we are comparing 1 and 2, so one will be the project with a lower cost and the second one is a project with a higher cost. So we will compute delta C, that is the project associated, the total cost associated with the higher project subtracted from subtracted by the previous one. So we denote this as in the denominator what we call as C, delta C. So again we calculate the equivalent total benefits as we have done in the previous case, or the disbenefits associated with the alternatives, and we subtract the two to compute the incremental benefits. Okay, so if we are taken into account the disbenefits, so the same will be written as delta B minus D. Okay, so same ratio will be computed, that is delta B by C ratio, or if we are taken into consideration the disbenefits, it will be delta B minus D by C, and on the basis of the previous guideline, that is if delta B by C is greater than equal to 1, then a higher cost alternative will be selected. So it will be much more clear if we explain it with the help of an example. Say for example, if we are having two alternatives, one is a project associated with an open trench and another project which is associated with a tunnel trench. So different cost parameters are given, like the distance is given in miles, the first cost dollar per foot is given, so 700, and again for the tunnel it is given as for the first 2 miles this and for the remaining 4.3 miles this. Time to compute is also given 24:36. Construction support cost, Okay, so these are MNOs. So this is also given, and this is the ancillary expenses per month that is associated with the environment safety. So these are basically the benefits associated with the project. Okay, and the planning horizon is given as 50 years. The interest rate is given as 3% per year compounded annually, and this is the conversion. 1 mile with this is this much feet, and using B by C analysis, select a suitable alternative. So if we just compare this problem with the previous that we have discussed in part 1, so in part 1 what we have only one project, and we are basically computing whether to accept it or not, or rather in other words we can say we are comparing that particular project with a no project condition. So but here we are having two mutually exclusive projects, so we have to make a decision using the B by C analysis whether to go for an open trench or to go for a tunnel trench. Now let us make some calculations. So if we see since the project life in months is given, so if you see some of the data is given in months and the interest rate is given as annually, so we have to convert this month data into an annual basis. Okay, so let's convert it. So the first cost is given as $700 per foot. If we multiply these two, that is 700 into 6.8, so that will give us the total cost, that is 700 into 6.8, so that is in feet, and that is in feet, and since some of the data is in miles, so we are converting. Okay, so this is given as per feet and per foot, and this is given in miles. So 700 converted into miles, so we have to multiply this 700 by 5280 and multiply it by 6.8. So this will be the total present cost of the construction. Fine. So this is already the present cost, so no need of any conversion. But as far as the second cost is concerned, that is construction support cost, it is given as per month, that is 250,000. Fine. So 50,000 per month. So we have to convert this into a present worth method. We have to convert this at the present point of time. So if we just see 250,000, since it is given in months, so we have multiplied by 12. So these are the annuities extending up to 24 months. So 24 months means 2 years. So the thing is that we have to convert this we have to compute this, or these annuities will extend up to 2 years. So if we just see, this is the total cost in year, and we have to compute P, and this is A given, and the interest rate is given as 3%, and since the time duration is 24 months, so equivalent we have 2 years. So if we just compute this will be the present worth of the project of open tunnel. Now the thing is that this is the data for 2 years, but the project life is 50 years. So what we have to do, we have to convert this on a 50 years basis. So if we have this figure, if we just convert this open tunnel, so in terms of annuity, so the present worth is given, so we are interested in finding out where annuities are given, we are present worth is given, we are interested in finding out annuities. So we can use the relationship between P and A. So P is given, we can find out A, interest rate is given as 3%, and the time of the project is 50 years. So if we just compute this with the formula what we have discussed earlier, so it comes out to be $1.2 million per year. So this is the annual worth associated with an open tunnel project for a lifespan of 50 years. Okay, so we have converted the data into an annuities for a period of 50 years. Similarly, for the second option, that is the trench tunnel. So in trench tunnel, the cost is given as for 700 miles, it is $700 for the initial 2 miles. So you convert 700 into feet, multiplied by 2, and for the remaining 2100, you can multiply it by this and 4.3. So that will be the present worth. And of course, the second thing, on similar lines, we have to convert the additional expenses at the present point of time. Here if we see, the time duration is given as 36 years. So 36 years mean 3 years. So if we just compute the present worth, it will be this plus these are the annuities given. So we have to convert these annuities into present worth. So A is given, we have to find out P. Interest rate is 3% and the project duration is 36 months, or we can say it is of 3 years. So if we just compute this, so the present worth of tunnel trench comes out to be $61,010,460 $61,10,460. So again, this is, we have evaluated this for 3 years or 36 months, but the project duration is given as 50. So we have to convert this present worth into annuities up to year 50. So the thing is, we use the relationship between A and P, where P is given and we are interested in computing A. The interest rate is given as 3% and the time of the project is given as 50. So if we just convert this present worth into annuities for over a period of 50 years, it comes out to be $2.37 million per year. Now, if we see which one is having the lowest cost, that will be written first. So if we compare the two, the tunnel trench alternative has the larger equivalent cost. So we will write this as the second alternative. First alternative will be the open trench. So the incremental cost can be computed by subtracting the total cost for the tunnel trench, by subtracting the total cost of the open trench with the tunnel trench. So this minus this will give us the delta C for this particular, when we are comparing the lower option with the highest one. So the lower option is here in this case is the open tunnel, and the higher cost option is basically the tunnel trench. So we are comparing this open tunnel with a tunnel trench. So if we just find out what will be the incremental cost when we are comparing the two, if we subtract these two, it comes out to be $1.17 million per year. Similarly for the benefits, so if we just see the benefits per month benefits are given. So for 24 months, these are the benefits, these are the annuities for the month for 24 months are given, and for the 36 months for the tunnel trench is given. So if we just convert it in terms of annuities extending up to years 50. So for open tunnel, if we add all the three, that is this plus this plus this, so this comes out to be 310000. 310000. So converting into an year, so multiplied by 12, and these are A is given, we are interested in finding out P. The interest rate is 3% and the time is given as 24 months, so that is 2 years. So this is the present cost associated with the benefits up to 24 months. Converting this into annuities extending up to 50 years. So this is the annuity given, this is the present worth given, we are interested in finding out P. So P is given, we are interested in finding out A. The interest rate is given as 3% and the time of the project is 50 years. So if we compute this by using the relationship between A and P, where P is given, we can find out P. It comes out to be this much. Similarly for the tunnel trench, the total benefits is nothing but if we add all the three, 50, 60, 70, 75,000. So if we see 85,000, 50, 60, so there might be some calculation error. So 60, 70, 85, 80, 85. Okay, so this is 85,000. Okay, fine, this is 85,000, that's correct. So 85,000 in months, so just convert it into years by multiplying 12. So we are interested in finding out P, where A is given, the interest rate is 3% and the time duration is given as 36 months. So it will be 3 years. So this will be the present worth for 3 years cash flow. And when we convert this thing for 50 years, and in this P is given as this much. We are interested in finding out A. The interest rate is given as 3% and the time duration is given as 50. So if we just compute this, this comes out to be this much per year. Now if we are interested in finding out the incremental benefits, so the incremental benefits, if we subtract this much from this, so the benefits comes out to be this. Now if we compute the incremental benefit to cost ratio, this is 0.16 divided by 1.17, so it comes out to be 0.14. So the conclusion is that if we are comparing among the two, so the larger cost alternative is not selected. So in this case, since the B by ratio is coming out to be less than 1, so the higher cost alternative, that is the tunnel trench, is not economically preferred. Thus the answer to this is that we have to stick with the less cost option, that is the open trench. So in this case, there is another term. This open trench is basically the defender and this tunnel trench is basically the challenger. So if B by ratio is coming out to be less than 1, then the conclusion is that we have to stick with the defender, and if it is coming out to be greater than equal to 1, then we have to switch over, or we have to drop the defender and we have to opt for the challenger. So in this case, the tunnel trench is basically a challenger which is dropped because the incremental benefit to cost ratio comes out to be less than 1. So we will be sticking with the defender, that is the open trench. So that is how we solve the problems when we are having two mutually exclusive alternatives on the basis of incremental benefit to cost analysis. Now if we have more than two options, n number of options, or 3 or 4, whatever, so what we will do, we will extend what we have discussed so far. So the thing is, here what we have to do, we have to just compare step by step, one option compared with the second one. Then we will be selecting one among the two on the basis of incremental B by C ratio. Then once it is being selected, then we compare this with the third one. Again, the selected one will be compared with the fourth one, so on and so forth. So this is the same procedure what we have discussed in our previous slide, what I have just told you in our previous slide. The only thing is that here we have to compare step by step. So in that case, we are having only two, so there's single comparison, but here we have to compare multiple times until unless all are eliminated and we have only one option left with us. So this is the procedure, the same what we have what we have in our previous slides. So it's better if we just compare it, or we can just see it with the help of an example. So if you just see this example, so not going into the text, simply what is given is that a water park is to be established and the options that it can be established in any one of the 4 cities. The associated costs are given. Okay, first cost is given, entrance fee cost is given, revenue is given, initial cash incentive is given, property tax reduction is given, sale tax sharing is given. So accordingly we have to decide that what are the total cost and what are the cost associated with the benefits. So it will be, we have to first see what are the benefits here and what is the total cost. So if we carefully see that this is the cost or the expenditure and this is the expenditure, the first two are basically the two terms which will be contributing in C, and rest of the things, that is available revenue, this is the benefit, initial cash incentive, this is also a kind of benefit, then reduction in tax, this is also a kind of benefit, and sales tax sharing, this is also a kind of benefit. So rest of the four lines, they basically represents, or we can take these 4 into consideration when we are computing the benefits, and the first two, they are important for evaluating the cost. Okay, so again B by C analysis is to be used to find out that which is the best city for which this project can be installed, and the interest rate is given as 7% per year and the study period is given as 8 years. Fine. Now there are some cost, like this is one time investment which is given at in a cash flow, it is given as 0.0, but rest of the things, some of the costs, they are expressed on the basis of per year, and some are not expressed, like initial cash incentive, this is one time, and rest some of the costs, they are expressed in years. So we have to convert all these things on identical lines. So I have used an Excel sheet to solve this problem. So let us see. Now this is the Excel sheet. So if you just see, the first cost is given. So I have the first two rows, they are basically the two points or the two things which will be contributing towards cost, and rest of the 4 points, rest of the 4 items will be contributing towards benefit. Fine. Now the thing is that if we some values are given on per year basis, so either we convert all these things on per year basis, or we just convert all these things on in the form of present worth. So let us choose on an annual basis. So the thing is, if we just convert this first cost on an annual basis, so how we can convert this? So just see, this is the first cost given, and the project life is given as okay, the project life is given as 8 years. Fine. So if I just convert this thing in terms of annuities, so you see what I have used a formula where P is given and I am interested in finding out A. So A will be P I 1 plus I to the power n. Same formula which we are using earlier, same is applied here also, and I have written this one. So it will be P is given, and I am simply converting this thing into annuities. Okay, so if I just convert this thing into annuities, and entrance fee cost, this is given in terms of per year, I think so. This is already given in per year, so no need of converting this entrance fee. So the thing is, this is already given in, okay, I should write here as per year, itna $1 million per year. So if I just compute the total cost, so equivalent of this present worth into annuities, that I have done from here to here, and plus, since this is already expressed in on a year basis, so just add these two costs. So if we just compute this comes out to be 6.98. Fine. This is in million of dollars per year. So I have converted these two costs on an year basis, and I have basically added these two factors into one and computed the annual cost associated with the project. Similarly for city 2 we can compute, similarly for city 3 and 4. Now next comes the revenues. So the annual revenues, they are given in per year. Okay, so no need of converting it, they are already given. Now initial cash incentive is given as one-time investment, so we have to convert this one-time investment on a year basis. So if you just see, this is the investment given as per year basis, so I have used a same formula for converting this present worth into annuities. So the same formula is being applied, that is P equal to A 1 plus I. So here in this case P is given, I can easily compute what will be the value of A. I is given as 7%, that is 0.07, and N is given as 8 years. If we just put the numerical values in this, so easily we can find out what will be the value of A. So if I just use this formula, so applying the formula here and computing, this will be the initial cash incentive on an year basis for an 8-year economic life. Similarly for B we can calculate, for city 2 we can calculate, for city 3 and 4. Now tax reduction, it is already given in years, no need of any conversion. Now the thing is, if we just see the total benefits or the total annual worth associated with the benefits, we will be adding this plus this plus this plus this. So if you just see, I have sum it, this one B13, this one, okay, already in here, and rest of the things they are added, and this I have already converted this present worth into annuities. So this annuity plus this, if we add all these four things together, so this will be the total cost associated with the benefits. So this is the total cost associated with the benefits. Since we have expressed the total cost in terms of per dollar million, so I convert this into millions, so this comes out to be 7.37. Similarly for city 2, city 3 and city 4. So the first step, so once we do these calculations, the very first step is, so if we just see that this is the total cost associated with the project, and this is the total benefit in terms of costs which are associated with the project being installed in different cities. Now the very first step, when we have such data available with us, the very first step is that we will compute the B by C ratio. So for city 1, the benefits comes out to be this one and the cost comes out to be this one. So if we see this divided by this, so this divided by this, so B by C ratio, it comes out to be 1.062. Similarly in this case, what we will do, we divide the benefits, that is 6.614 divided by 7.165. Similarly for city 3 and city 4. So if we just see, this is the only benefit to cost ratio which is coming out to be less than 1. And okay, before that, one thing more, that once we get all these things, once we get the cost, so we have to arrange the projects, arrange the cities in such a manner that the minimum cost project will be listed 1 and the maximum cost project will be listed 2. So because in this case there is no shuffling of any city, so that is why city 1, the order remains the same, okay, because this is the minimum cost, next highest is this one, even next highest is this one, and the highest among the 4 is this one. So these cities, they are already arranged, so no need of arranging it. If we get somehow different values, then we have to arrange the cities in such a manner that the minimum cost project will appear first and the maximum cost project will appear at the last. Now once we calculate B by C ratio, the very first step what we will do, we will eliminate that city where the B by C ratio is less than unity or is less than 1. So here in this case, if we see for city 2, if we calculate the overall B by C ratio, it comes out to be 0.923. So this will be eliminated in our calculations. So we can simply eliminate this. Okay, so this will be eliminated. Fine, I have already written here, this will be eliminated. Now we left with the choice among the 3 cities, that is city 1, 3 and 4. Now how to make decision regarding which city will be preferred after eliminating city 2 on the basis of overall B by C ratio. Now what we will do, we will compare this city. So in this case, what we have another situation what we call as, if we don't install the project in any one of the city, we call it as DN. So if we compare this with DN, or simply we can say that while making comparison for city 1, we are basically comparing the DN condition with city 1. That is a situation where we don't have any project in any of the city and having a project in city 1. So in this case, DN is basically the defender, and we are basically compare this defender with the challenger, and here in this case the challenger is city 1. So we have to make a decisions whether we have to continue with the defender or the challenger is accepted. So that we can do with the help of incremental benefit to cost analysis. Now if we just compare, so DN conditions, all these costs will be 0 obviously. So if we just compute the incremental cost of city 1 by comparing this with the DN condition. So the thing is, here the annual cost is 6.948 and in the DN condition the cost is 0. If we subtract the two, so this will be delta C per year. Similarly, the benefits associated with city 1 is this. The total benefits associated with this city are these in terms of monetary value, and of course for the DN condition we don't have any benefits, so it automatically it will be 0. So 7.377 minus 0, so delta B that comes out to be this much, delta C comes out to be this much. Now if we compute the incremental benefit to cost ratio, so this will be 3.377 divided by 6.948. okay, so if we compute this comes out to be greater than 1. So whenever this comes out to be greater than 1, I've already told you in the previous video that the higher will be accepted, higher cost option will be accepted, or we can say that the challenger will be accepted. So here in this case the challenger is city 1, so we will drop the DN condition and we'll accept among the DN condition in city 1. On the basis of this incremental B by C ratio, we can say yes, the investment in the higher cost project is justified because the incremental B by C ratio is greater than 1. So we will not continue with the defender, rather that the challenger will be accepted. So the answer to this comparison is, that is from DN condition to city 1 we will be working for the project in city 1. So the selected city will be 1. So we have, in this case what we do, we have dropped the DN condition, what we call as a defender. Now we are working, now the project can be worked out in city 1 as compared to DN condition. So now this will become the new defender and this is to be challenged with the remaining 2 or 3 whatever we have. So the answer, if we just compare this one, city 1, so we have selected city 1. Now since city 2 is already eliminated, so no need of making further calculations, just coming on to city 3. So on the similar lines, if we have already made computations regarding the annual worth and the total benefits, and overall B by C ratio is greater than 1, that is why it is not being eliminated. So if we just compute the incremental cost, so what we are doing, we are basically comparing city 1 with city 3. So the incremental cost is nothing, but if we just see, it will be a difference of these two, this minus this. So this is the incremental cost difference. So if we just see, the incremental cost difference is this much. Similarly for the benefits, if you see, I have subtracted the two benefits, the one with the higher cost with the one with the lower cost, or from the challenger we have subtracted the defender. And again if I compute the incremental B by C ratio, it comes out to be greater than 1. So once it is greater than 1, that means the highest cost option will be selected. So in this case, this one is the highest cost option as compared to city 1. So the defender is to be dropped and the challenger is to be selected. So among selecting from city 1 and city 3 on the basis of this, the result will be that city 1 will be dropped and city 3 will be selected. So the selected city will be 3. Since B by C ratio, incremental B by C ratio is greater than 1, so higher investment is justified. So what we did, we dropped city 1 option and we have selected city 3 option. Again, since we left with one more city, similarly city 3 will be compared with city 4. Now city 3 is the defender and city 4 will be the challenger. So the comparison is to be made as 4 as the challenger and 3 as the defender. So just compute the incremental cost difference. So it will be this minus this. Similarly, incremental benefit difference, it will be this minus this. So it will be 0.5, and if I just compute the ratio, it comes out to be less than 1. That means if it is less than 1, then higher cost option is not selected. That is, the challenger is dropped and we have to continue with the defender. So here in this case, the defender is city 3. So here the option is again city 3. Now we don't left with any other option. So upon solving this, using the incremental B by C ratio and the overall B by C ratio, the answer to the problem is that for executing this project, on the basis of BPIC ratio, the city 3 will be selected. So this is how we use incremental benefit to cost analysis when we have multiple options. Somewhat similar what we did in case of two alternatives, and here we are just comparing in steps. So this is all about how we use benefit to cost analysis to answer such questions, that is which one is the best project to invest in if we are having multiple options, or if we are having one option, then we can make decision whether to go for the investment in that project based on the cost and benefits. So this is all about the benefit to cost analysis. Thanks.